Okay, Dr. Stuart.
Okay, thank you, James. Okay, welcome everybody to the LAFMAT seminar today. We have Professor Etienne Janod joining us. I'll just say something about the network itself before we start. The network is composed of several Latin American universities, including the following. I have a list. I'll just read out the list. Apologies if I mispronounce any university. We have the National University Mayor de San Marcos in Lima, Peru. We have the University Católica del Norte in Antofagasta in Chile. We have the University San Sebastián in Puerto Montt, also in Chile. We have Centro Atómico de Bariloche in Argentina. We have the University Federal de Pernambuco in Brazil. We also have the University Federal Rural de Rio de Janeiro, also in Brazil, and the University Federal Fluminense, Brazil. We also have universities in Colombia. We have the National University of Colombia in Bogota, and we also have the University del Zulia in Venezuela, and the University del Oriente in Venezuela. We also have the Centro de Estudios de Materiales Avanzados in Mexico and Sinvestav in Mexico. And also we now also have somebody from the University Autónoma de Nuevo León in Mexico. So welcome everybody. This week we have Professor Etienne Janod, and I will just briefly introduce the speaker and then the speaker will start. Dr. Janod was studying high temperature cuprates at the University of Geneva in Switzerland. He also did part of his PhD work in Grenoble, the CEA labs in Grenoble in France. He then worked as a postdoctoral research assistant in the University of California, San Diego, on the metal insulator transition, very interesting topic, I have to say, on doped amorphous silicon. He then came back to France. He joined the CNRS. CNRS is the Centre National de la Recherche Scientifique, a national research facility in France, at the Institut for Matériaux in Nantes, the city of Nantes. He was working on Haldane chains and quantum magnetism. In 2004, he discovered a series of materials in the chalcogenides that behaved as Mott insulators, and the transition between metallic and insulating state could be the transition was driven by an electric field. This led on to further research where this idea was used to create an artificial neuron, and that led into neural networks and low energy consumption neural networks. So I'm going to stop there and hand over to Dr. Etienne Janod. Please.
Okay, thanks a lot. So, hola a todos y gracias por la invitación y esta presentación. Me hubiera gustado hablarles en un idioma latinoamericano, pero dado mi nivel de español o portugués, es mejor que les hable en inglés. All right, so maybe now I will shift, and before, so yeah. Let me do things in the proper order. I will share my screen here and then do this. Okay, I think that's fine. It's good for you. I think you can. I guess you can see. Yeah, tell me if not. All right. So before I really start, I will introduce briefly the city where my laboratory is located. So as you can see on the map. Oh, I will use this. All right. As you can see on the map, it's located in Nantes. Nantes is on the west of France, very close to the Atlantic Ocean. And if you travel around the city, you will see a beautiful old castle, as you can see. And you might have the chance to meet the very strange big animal like this, a giant elephant, which is really one of the most famous thing in Nantes today. So our laboratory is located in this city. So this is the Institut of Matériaux, named after its creator, Jean Rouxel. we have more than 200 people working in this lab, including more than 90 PhD students and postdocs, and half of them are from abroad. And this lab is an interdisciplinary research lab in material science where we study well, electrochemical storage, the lithium battery, material for optics, thin film and plasma, and also we are studying metallurgy. But the team I belong to is physics of material and nanostructures. So today, the topic of my talk will be I will talk to you about quantum material, both on the point of view of application, but also on the point of view of basic science, as you will see. So this work, the work I will present is the result of really in-depth collaboration, let's call it like this, with our colleagues from Institute of Physics in Rennes, very close to Nantes. But also it's an international collaboration with Tohoku University in Sendai through an international research France, Japan laboratory dynamical control of material. And also a lot of the results that I will present have been obtained in large-scale facilities such as the European synchrotron ESRF, which is located in France, in Grenoble. Okay, so let me start by giving you some element of context. And this context is the context of the energy consumption of information technology. In fact, in 10 years ago, in 2015, let's say the energy consumption of information technology was, let's say, orders of magnitude below the worldwide energy production, which was not completely alarming at this stage, but in 10 years things have dramatically changed, and now we start, I mean, the energy consumption, it's between 5 and 10% of the worldwide energy production. And if we extrapolate this curve, we realize that in before 2040, the energy consumption of information technology will reach the current level of energy production, which is, of course, it will not occur, but it means that we have to do something. We cannot let the situation evolve like this. And at least the desired trajectory is to reduce this consumption by 1,000. So it's ambitious, but clearly scientists have to do something on this topic. And to understand why information technology consume so much energy, I propose you a kind of collective experiment. And so you just have to look at your screen, and this experiment will be done in 1 second. Okay, experiment is done. In roughly speaking 100 milliseconds, you recognize that this picture represents a snake. And if we ask either a supercomputer or a mouse to do the same task, recognition of this image, let's say, they will perform the same as you and me. In 0.1 second, they will recognize this is a snake. The big difference, however, is energy consumption, because the energy consumption for the visual system of the mouse is only, well, let's say the power consumed during this recognition task was only a few watts, whereas if for the computer, a supercomputer, the energy consumption would be 10,000 times larger. Why is it so? Why computers do consume so much? Why do they perform so poorly in terms of energy efficiency? In fact, the answer to this question is in the architecture of computers. As you might know, all the computers that we use today are based on the old von Neumann architecture, where basically we have one memory talking to one processor that treats the information, and all the operations are due in a completely sequential way. There is almost no parallelism in the way our computers are working. If we compare that to the architecture of the brain, Here, it's an artist view of what is relevant in the brain for this recognition task, which are on the one hand the neurons that treat the information. We will come back to this a bit later, and also the synapses that let's say store the information corresponding to the memory. And in fact, in the brain, we have billions of neurons and billions of synapses as well. But the information is treated in a massively parallel way. Uh, and in fact, this is because of this parallelism that gives this efficiency for certain tasks, such as this recognition task. So the idea to build up to build up computers to do computing with an architecture which mimic the architecture of the brain is already old. Actually, here you have just a schematic view on how synapses in blue and neurons in red are interconnected in a brain of mammalian. And the idea to use that is already old. And in fact, all the artificial intelligence application, ChatGPT and so on, that you all know today, are based on the software neural network implementation of these neural networks. And this is really a paradox, because we mimic this architecture, but we run them on computers which are with the classical von Neumann architectures. So that's why the need to use von Neumann architecture is the reason why it's not efficient at all. But there is another possibility, which would be, instead of using software neural networks, that would be to use hardware neural networks. The big difference is that for that, the idea is to rebuild computers with a completely new architecture, where really we need to implement artificial neuron and synapse. So therefore, if we want to go towards a potentially highly energy efficient artificial intelligence in the future, a possible way to, if you want to do that, you have to meet two challenges: is to implement artificial synapses on the one hand, and implement artificial neurons on the other hand. Okay, so and we propose for that to use the properties of quantum material, and this is what I will talk to you about in the next slides. Right, but this proposition is not our proposition. In fact, a few years ago, colleagues from Japan, Professor Tokura and colleagues, published in Nature Physics a nice review article called "Emergent Function of Quantum Materials." And well, I mean, you probably all know that quantum materials are the materials that cannot be described by the classical band theory that explain most of the property of the solids, but some solids cannot be explained by this classical band theory, and that's what we call the quantum material. So it includes material with strong electronic correlation on the one hand, and material with topological property. So, and what this Japanese colleague has proposed is that we should use the electronic, well, the properties, the emergent properties of this material in order to build up new fields of application. And that's why they name a few, as you can see here, like topological electronic, quantum computing, and so on. But one of the domains they explicitly mention is motronics. In other words, it's the use of the property of MOT insulators in the field of microelectronics. So let me explain a bit, and let's start with the beginning. Let me explain what are MOT insulators. So if you consider a system which has on average, let's say, let's consider a half-filled system. That is a system for which the last band, the one close to the Fermi energy, is half-filled, only which has one electron in the last band. In this case, electronic delocalization is usually allowed, and if in terms of density of state or spectral weight, the last band is half filled, the Fermi level is in the middle of the band, which has a width W, and you end up with a metal. This view is predicted by classical band theory, is correct as long as the one parameter use the electron repulsion on site is lower than the bandwidth. It's the case in many systems, but in the large class of material called MOT insulators, this is no longer true. And in this system, essentially with a system in which you have 3D or 4F electron close to the Fermi energy, these electron repulsions become so large that having two electrons on the same side, having a double occupancy, costs too much energy, and electrons prefer to be frozen on their side, and the systems it ends up with an insulating state. So what it means is that the half-filled band predicted by classical band theory is splitted into two sub-bands called the lower and upper Hubbard band. And these two bands are separated by this energy electron-electron repulsion U. And if the electron repulsion is big enough, then you might have a gap between the lower and upper Hubbard band, and therefore an insulator. This is what we call MOT insulators. Of course, the two cases that I describe here are the two limiting cases, and you have situations where U and W are close to each other, and then you have nice new properties that emerge. For example, you have very strange metals that appear when we are in this limit U and W close to each other. You have quasi-particle peaks that emerge in between the lower and upper Hubbard bands. And yeah, this kind of metal have also interesting property, and that leads to many interesting things, such as ITC superconductivity, for example. And you can easily realize that when, as on the left we are metallic and on the right we are insulators, there is some value of of the U over W ratio for which we will have a metal to insulator transition. In fact, modern theory modern theory of band structure calculation that are able to take into account this electron repulsion are now able to predict the phase diagram of such MOT insulators. In fact, what they do predict is that, let's say, when you take a MOT insulator at low pressure, you are in this MOT insulating state with a gap between the lower and upper Hubbard band. And once you apply a pressure, you increase the bandwidth of your system, essentially. And if you increase W enough, then you might close the gap and end up with a metallic state. And in between these two states, you have a first order transition line called the MOT line this line ends up at a critical endpoint, which is a second order transition point. Right. In fact, let me mention here a few examples of real systems that really illustrate this concept and this reality of MOT insulators. And among them, we can cite the V2O3 system doped with chromium, which is studied since more than 50 years. But also, I would like to cite another family, no longer an oxide, but a chalcogenide system. Q is indeed a chalcogen such as sulfur, selenium, or tellurium, and this family AM4Q8. Yeah, we have studied. You will see some results that we obtain on this system. All right. So, and just to illustrate the fact that the real phase diagram correspond indeed to the one predicted by modern theories such as dynamical mean field theory. Here you have the phase diagram of the V2O3 system, and you recognize at room temperature two phases, Pi, like for paramagnetic insulator, meaning MOT insulator, PM for paramagnetic metal, so it's metallic indeed. And you recognize in blue here, almost vertical, the MOT line, the MOT transition line between the MOT insulator and metallic state. And when we apply a pressure, we cross this line, and we have a drop of electrical resistivity by several orders of magnitude. And so it's a first order transition. From the electronic point of view, it's clear that we have a big jump. And if I look now on from the structural point of view, here you see that the volume, the unit cell volume of the material also drop in a first order way, let's say, by -1% close to room temperature. These are experiments obtained by Julio Guzman during his PhD. All right. So, but all this, it's let's say classical example of MOT system and classical way, let's say, to induce insulator to metal transition. It's by pressure. But what we have discovered in our lab is something that goes beyond that. We have observed that by using another stimulus, electric field, we can also achieve this insulator to metal transition. So let me show you what we have done. So we have first worked on a single crystal of this gallium tantalum 4 selenium 8 compound. We have just mounted electrodes, and then we start to apply electric pulses. So here you see in this example, when we apply a pulse which is not very intense at low voltage, the resistance that we read during the pulse, that you can see here, you see it's a pulse of 10 microseconds. The resistance is the same as the low bias resistance measured before and after the pulse. Don't pay attention to this initial part, it's just a capacitive effect. But what we have observed, which was a big surprise at that time, is that if we exceed a threshold value, a threshold voltage or threshold electric field, then look at what happened in the middle of the pulse. Here, after 4-5 microseconds, we have a sudden drop of the resistance here by almost 2 orders of magnitude, and the resistance really decreased a lot. And what is interesting is that when I stop applying the electric pulse, this resistance relaxes. We call that a volatile electric mode transition. But if we continue our game and further increase the value of the electric pulse, what we do obtain, we obtain the same transition. So it occurs here in the very beginning of the pulse, and then the resistance stay low during the pulse. But after the pulse, the resistance remains in its low resistance state. We call that a non-volatile electric mode transition. And what we have discovered is that this property is not specific to one specific MOT insulator, though it's GATA4SE8 that I show you just on the slide before, but it also occurs in all the MOT insulator we have tried. This oxide, V2O3, it works. It works also on another canonical MOT insulator, nickel disulfide, substituted with selenium. We have this, you see here the drop of resistance, but it works also on molecular MOT insulator. This is the example shown here. And this is universal for the volatile part that I show here, but it's also true for the non-volatile. Here I present resistance versus temperature measured before in red or after in blue the application of the electric pulse, and you see that after the non-volatile transition, we have a permanent decrease of the resistance. So this property is universal in all in all MOT insulator. They can be chalcogenide, oxide, or molecular. It seems that it doesn't matter, let's say. All right. So, and in order to understand better what is the mechanism which is behind, we have worked on the AM4Q8 system, and we have used the richness of the chemistry of this family. But you see, we can change the metal, vanadium, niobium, tantalum, or we can change the chalcogen, sulfur, selenium, tellurium. And it's nice because it allows us to tune the value of the Mott-Hubbard gap. So what we have done, we have studied the value of the threshold field that I just introduced in the 2 slides ago, and we have plotted the evolution of this threshold electric field as a function of the gap of the material. And here is the result. The larger the gap, the larger the threshold electric field. And this behavior, you see that we have observed that we can describe, roughly speaking, this behavior with a power law, and let's say a power close to 2.5 was able to describe the data. Why is it interesting? Because if it corresponds to a behavior which is well known in semiconductors. And in particular, what is known in semiconductors, there is an interesting phenomena which is known in semiconductors, which is called avalanche breakdown, in which when you apply an electric field in a semiconductors, you will accelerate electron and you will have impact ionization effect that will multiply the number of carriers in such a way that at the end, you end up with a metallic state. And this is the evolution of threshold field as a function of the gap in these semiconductors. It's a log-log scale, so you see that this power law correspond to a straight line in blue. And you see that the point in these classical semiconductors, it reproduces what happened in this family of system. But you see that here I had a data point, and it matched nicely on this curve of classical semiconductors. So this is some kind of evidence that probably an avalanche breakdown is also at the origin of what we observe in a system which are narrow gap MOT insulators. So this was the electronic part, but we also try to understand whether from the structural point of view, whether this transition has some consequence. And for this, we have done micro X-ray diffraction. Here, I show you an example. So this stripe at the center corresponds to a thin film of V2O3 that we have deposited. And in yellow, you have the two electrodes, and we have applied an electric pulse to induce a non-volatile transition. And after that, without applying electric field, we have done a mapping of the unit cell parameters thanks to a micro focused X-ray beam. And what you see is that, okay, I will not explain here the contrast in the domain which are not affected by electric field, but what you can notice that here on this side, you have appearance of a domain for which the unit cell volume is compressed. And this is interesting because this behavior strongly recall what we have when we cross the insulator to metal transition. I shown you the compression that occur at the transition between insulator and metal. And here we find exactly the same kind of behavior when we apply electric field. But basically, you also see that this compression do not occur as a bulk phenomena on all the samples in which an electric field was applied, but it occurs in a filament. So, in fact, in order to confirm that, we have done some simulation. I don't go into detail, but let's say, as you can see on this animation, this simulation confirms that most likely it's quite normal that the mechanism, let's say this transition, insulator to metal, occurs through the formation of a filamentary conducting path. All right, so at this stage, what we can say is that we have discovered what we call resistive switching effect with with a distinction: non-volatile transition and volatile transition. And what I will show you now is that out of these two properties, we have been able to build up or to implement two different, let's say, application. For non-volatile transition, it was MOT memories and MOT synapses, and for volatile transition, it was MOT neuron. Let me start with MOT memory and synapses. So, if we want to go into the field of microelectronics and build up new memories, we need to go to thin film. So here, of course, so that's what we have done. So you can see the typical thin films that we have been able to grow. So as you can see, it's not epitaxial, it's granular films that we obtain. And by, let's say, using the proper pattern substrate, here we use substrate where we have electrodes in yellow. We deposit the film in red and deposit an electrode on the top. It's quite easy to apply electric pulses that will change possibly the resistance of this small part shown with my laser pointer here. And this this allow to check the property, but at a very low spatial scale. And what we have seen is that when we do that, you see that we have been able to induce a drop of resistance by applying an electric pulse initially. But what was extremely interesting is that the application of a further electric pulse allowed the system to go back to relax to its initial state. What we believe is that this effect, what we call the reset transition, is not due to the same phenomena, but it's due to simply to a Joule-heating effect that relaxes the system back to its initial state at equilibrium. And what you see in this example is that the duration of the pulse that allows to do this transition in these really tiny objects, in which this typical size is a few hundred of nanometer. In fact, the energy which is required to do this transition is quite low, typically around 1 picojoule. And this is due, of course, to the fact that the energy that is consumed correspond to the current times the voltage, but times the duration of application of the pulse. And as the duration of the pulse is very low, then the energy is of course low as well. So after this proof of principle, let's say we have been able to test different MOT insulators, GAV4S8, the family I already mentioned, and the V2O3 system with V2O3 doped with chromium, and working on such systems, we've been able to starting from this system, we have been able to go higher in size, and we have been able to deposit this layer of material on big wafers, which are at the level of microelectronics. So you see it's 8 inches, 20 centimeters in diameter of these wafers. And what you see in this image here, you see in this yellow rectangle, it's where the film is located. But what this work is, let's say, demonstrate is the fact that all what we do, I mean, the deposition, the annealing treatment that we do are compatible with the requirement of microelectronics. And that's why we are engaged in collaboration with companies such as ST Microelectronics. All right. Just in terms of performance, let's say that this memory part, let's say that the endurance of this memory is quite good. We can cycle over more than 10 to the 5 cycles. It's also the writing and erasing voltage are quite low in the 2 to 4 volts. As a comparison, the flash memories that you use in your computer, in your cell phone, the amplitude of the pulse is much higher, around 10 to 12 volts, just to write or erase an information in the memory of your cell phone. And also the writing and erasing time, I already mentioned that, but typically it is of the order of 100 nanoseconds, but we can even go lower. And once again, it's better, it's much shorter than what happened in flash memories. Okay, this is it for memories. But what is interesting is that when you are able to get a memory out of it, you are not very far from being able to build up an artificial synapse, because an artificial synapse it's almost the same as a memory, except that instead of being able to stabilize 2 levels of resistance, what you want to have is to have a continuum of level between a maximum and a minimum. And you see that in this experiment, in fact, we have proven, we have shown that it is possible. So clearly, we have a proof of principle that we can implement artificial MOT synapses. All right, so now let me switch to the second part, the fact which is more complex actually, is can we implement an artificial neurons by using the volatile electric mode transition? In fact, before going to that, I will just recall how a biological neuron is working. So here you have an artist view of biological neurons, but in the biological neuron, information is exchanged through the circulation of electric pulses. And this neuron represented here, each time he receives an electric pulses from other neuron connected to him, you have a voltage called a potential membrane, which increases. So each time an electric pulse is coming, you have an increase of this potential membrane, and in between we have a relaxation. And this process occurs. And essentially nothing happens up to a point where a threshold voltage is reached. And when this threshold voltage is reached, then the neuron itself emits an electric pulse and send him to all the other neurons connected to him. All right. So in fact, the question is, can we do the same with the electric mode transition? So in fact, to summarize things, what we want is something like this. Like we want, as an input, we need to send electric pulse to artificial neurons, and the output response that we would like is that we can have nothing up to a point where we reach a kind of threshold and we have emission of a signal. That's what we would like to have to mimic the behavior of a biological neuron. And look at what we have done. So we have tried to do the same. So we have, for example, in this example, we have sent 4 pulses or 6 pulses in a burst mode. And you see that in this example, nothing happened during the first 3, or nothing happened during the first 5 pulses, but on the pulse number 4 or on pulse number 6, we have just, in fact, the insulator to metal transition that appear, creation of the conducting filament, giving rise to a burst of current flowing through the sample. So in fact, this is interesting because it's a proof of principle that we can implement artificial neuron out of mode insulators. Of course, well, what I show here, you might have noticed that the voltage that I apply are extremely high, 50 volt, and current are also very, very high. So, and moreover, this experiment were obtained at low temperature. So it's not really useful for microelectronic application. But what we have shown is that after downscaling and using no longer crystal, but thin films, you see here, it's a view where on the right and on the left, you have the electrodes. And if we downscale this quite a lot, so you see inter-electrode distance is now 1 micron, and we can go lower than that now. You see that we recover, first of all, we have a strong reduction of the operating voltage. And on the other hand, these devices are working at room temperature. So we have the proof of principle that mode artificial neurons are well adapted to the constraint of microelectronics. So now we are working in order to create to put together, let's say, the synapse on the one hand and the neuron on the other hand in a single device, which is a complete hardware neural network based on mode insulators, based on artificial mode synapses and mode neurons. So that's the current job, and we have demonstrate recently that a simple recognition task like recognition of letters, which is the simplest thing that hardware neural network is supposed to be able to do, our system do the job. I mean, he is able to do this kind of recognition. All right. So before leaving this application-oriented part, let me show you a last example. Remember, I told you that the mechanism behind the electric mode transition is most likely something which is close to an electronic avalanche effect that leads to a multiplication of the number of carriers. But if you think 1 minute, if the key mechanism that leads to this insulator to metal transition is the multiplication of carriers, you might suspect that light can do the same. So in fact, what we have done an experiment where on the one hand, we apply electric pulses and also we synchronize these electric pulses with ultra-fast light pulse, a light pulse sent by a pulse laser of duration, roughly speaking, 100 femtosecond. So we have done an experiment which is a bit similar to the one I showed 2 slides ago. That is, we have sent electric pulses and we have chosen condition in such a way that nothing happened. You see, we have applied 5 pulses, as you can see here, and essentially no transition occurs between these 5 pulses. But if on top of this we send a single laser pulse at the beginning of the first pulse, as you can see here, you see that on the 5th pulse, we have this insulator to metal transition that occurs, which it's indeed an indication that multiplication of carriers promoted by the laser, both phenomena, both stimuli, light and electric field, work in a synergetic way. And in fact, for the future, this might pave the way or open the possibility to obtain a pure optical artificial neuron. Right. So now let's switch to something which is more basic science. With, for example, a basic question that you can ask yourself is especially if we can use light to do the same, what is the shortest switching time of this mode device? That is, what is the shortest time we need to that is necessary to go from the insulator to the metallic state. And if we can answer this question, if we can observe this, what are the mechanisms behind? That's the kind of question we ask ourselves. And of course, if we want to study that, we need to replace the slow electric pulse stimulus that it's very difficult to go below the nanosecond range with electric pulses. We can replace them with ultra-fast light pulse, because as you might know, it's now possible to use light pulse as short as a few tens of a femtosecond to tune the property of materials. So that's what we tried to do by working in strong collaboration with our colleague from Rennes and also University of Tokyo and University of Tohoku in Japan. Right. So first question, first of all, can we induce an insulator to metal transition with ultra-fast light pulse? So this is the question. And I briefly recalled the kind of technique we use to answer this question. So we use, let's say, what we call the pump probe technique. So usually we have a sample here. We send an ultra-fast laser to the sample. So a laser which duration is lower than 100 femtosecond. And soon after that, with a control delay, we send another pulse that we call the probe. It can be an X-ray pulse. It can be another light pulse, laser pulse. And then here I give you an example of what happened when we send a laser pulse. For example, we can do diffraction of the material. You see here, you see the Debye ring corresponding to the diffraction ring associated to the material. And we can study both the evolution of the electronic property, if we do pump probe in optical reflectivity, but we can also probe the structural evolution with a time resolution which is way below the picosecond. And that's what we have done in many places for studies this structural evolution. So we have done time-resolved X-ray diffraction in the European synchrotron in Grenoble, but also in Sweden on the femtomax beamline, and as well in Japan. Here is a picture of the X-FEL the Japanese X-FEL called SACLA. All right. Then, okay, and all this, all what I'm going to talk briefly now is we have published that last year in this article published in Nature Physics. So let me be a bit more specific. So what we have done, we have we have used the V2O3 system, so you know this V2O3 system. And let me recall that in this system, we can, the metallic to mott insulator transition, when we cross this transition is completely isosymmetric. So it's isosymmetric from the electronic point of view. We have an insulator, metal to insulator transition, which does not break any symmetry. And we have also a change of lattice, but the change of lattice is only a volume change without any change of symmetry. So it's a purely isosymmetric transition. And if we continue the trip in the phase diagram, if we cool down, we cross another line, which is the PI to AFI transition line. This line is purely symmetry breaking. That is, there is a first symmetry breaking, which is magnetic long-range ordering. And also, there is symmetry lowering. You see, we go from a trigonal to a monoclinic space group. So what we call that a ferroelastic transition. And therefore, if we go from here to here by crossing these two lines, you will not be surprised that if I go from here to the same final place, but by crossing this line will be more complex and will gather, let's say, the isosymmetric and the symmetry breaking transition. So indeed, here we have metal insulator and volume change, but also magnetic ordering and ferroelastic transition. Okay, so the question is whether what we study is that if we are in this low temperature phase, can we induce a transition from this anti-ferromagnetic insulating state to something which is metallic-like? So we have studied granular films that I already shown you, and their typical thickness were a few hundred of nanometers. But what you have to keep in mind is that the ferroelastic domains, that is domains that appear inside of the grain, are in the 20 to 25 nanometer range. So to check if we can induce an insulator to metal transition, our colleague in Japan have done the following experiment. So they have studied the reflectivity at steady state at room temperature, red, and at very low temperature in the insulating regime. You see these two colors correspond to these 2 points. And when you have these two reflectivity spectrum, you can easily deduce the variation, delta R over R. So this variation is the variation expected when you go from insulator to metal. The spectrum should evolve, should be like this. And in fact, what is remarkable is that the new points that do appear correspond to the points that are obtained after photoexcitation by a laser with a fluence of 7 millijoule per centimeter square, which correspond to roughly 4 photons per 100 vanadium. And in fact, you realize that the two curves are perfectly superimposed. It's a direct proof that by applying electric pulse with a fluence which is not so large, it's possible to completely generate an insulator to a metal transition. And in fact, okay, this is the electronic response, but we have confirmed this response, this electronic response by the structural. The structural response confirms exactly this scenario. Here you see the XRD pattern without, at rest in blue and after photoexcitation, and in this case, after 100 picosecond, you see that a spectacular evolution. You have a shift toward IQ, which means a compression. And also in blue, you see that the 3 monoclinic Bragg peak that merge into a single one as expected if we have a transition from the monoclinic to the hexagonal phase. So I don't go into detail, but trust me, in fact, the transition is complete. We have a complete transition, both on the structural point of view and also from the electronic point of view. In fact, now I will just recall something a bit more theoretical. What if we, when we send the laser to a material, what is quite known is that the energy can be transferred into electrons and stay in the electron channel, especially in insulators. If you are in a metal, rapidly the energy of the electron will be transferred into phonons. Phonons, it means it will generate incoherent phonons. And by doing so, in fact, you generate some kind of mechanical stress that for the phonon part is usually tensile, but for the electronic part can be tensile or compressive. And this mechanical stress is relaxed by the propagation of a strain wave that start from the surface of the material. Here, I explain what I just said. After a few tens of femtosecond, you have creation of this stress, and the profile of stress correspond to the penetration depth of light. This is the surface of material, and when you go on the right, you go to the core of the material. And after, and then we have launching of a strain wave starting from the surface. So you see that this strain wave, you have the surface that deform first, and here this is the front of the strain wave propagating, and this is what happened with time. And at the end, you have the propagation. The stress is now zero, but you see that we have a constant strain that will stay during typically that might stay like this during a few 10 or 100 of picosecond. So, and if I do a full image, let's say this might be like this in the case of a compressive strain wave. Okay, so this phenomena is quite known. This strain wave mechanism is quite known, but the question is what is not known at all. Can this phenomena carry with him a phase transition? And in fact, to answer this question, we need to look at a time trace of the evolution. Here, what I show is the evolution of the width of this peak that narrows after due to the insulator to metal transition, is the width of the 116 Bragg peak. And also I represent the volume, the unit cell volume of the material. Let's concentrate first on the narrowing of the 116 Bragg peak. What you see here is that after a few picoseconds, roughly 3 picoseconds, we have a full inversed ferroelastic transition, and we restore the asymmetry hexagonal phase expected in the metallic phase. In fact, what we propose is that within each ferroelastic domain, we have a propagation of a shear strain wave, that behave as in this small animation, and that restore that allows the system to go from distorted monoclinic to hexagonal. And if we calculate the time scale that we expect in such a scenario, we just have to divide the typical size by the propagation speed of transverse acoustic phonons, and we end up, if we do that, to 2 or 3 picoseconds, exactly the value we have experimentally. So, in fact, we have some kind of evidence that the monoclinic to hexagonal transition is driven by a shear strain wave within the ferroelastic domains. What you might notice now, if I switch to from the symmetry breaking part to the evolution of volume part, is that the volume has a waiting time of 9 picoseconds. To be honest, we don't know yet. We do not have a complete explanation of this, but what is quite funny is that between 3 and 9 picoseconds, the system has still a large volume corresponding to the insulating phase. But its symmetry has increased, and in fact we have a phase that looks exactly like the PI phase which exists in the phase diagram, and this behavior is completely impossible when we do only thermal. When thermally, this is not what happened. We never see the appearance when we warm up this system. So it's a regime it's a state that is accessible only through this excitation. Now consider the evolution of the volume. If let's say we have worked, as you might have seen, we have worked on 2 films of different thickness, 100 and 300 nanometers. For symmetry change, thickness did not play a role, and it's expected if things occur at the level of individual grains. But situation is very different for the volume change. You see now that the transition is faster for the thin film than for the thick one. And if we by doing the same game, if we divide the thickness by the time it takes for the transition to occur, we calculate a speed, and in fact this speed corresponds to the speed of sound. What it means is that it's again the propagation of a strain wave that propagates at the speed of sound. This is what we expect for a longitudinal strain wave, and this strain wave propagates let's say the structural transition volume change. So if I summarized that in this picture, first I have the photo excitation, then after 3 picoseconds, I restore my my asymmetry phase, but it's a PI-like the volume. It's a PI-like system. Then I have a waiting time up to 9 picoseconds, and then I have this propagation of a strain wave that starts from the surface and propagate through the sample up to the substrate. So this compressive strain wave is in fact the mechanism that drive this isosymmetric volume change. And what is even more interesting is that now if I compare this structural evolution that I just showed, this is the two upper panel, if I compare that with the electronic evolution, here I show you the reflectivity as a function of time for the film, which is 100 nanometer thick, you see that the dynamics for the reflectivity change, but therefore the dynamics for the electronic change from insulator to metal is exactly the same as the dynamics for the structural evolution. In fact, it means something which is quite amazing, is that the dynamics, the metallic state cannot be induced as long as the volume has not compressed in this V2O3 system. So I will now just conclude. So what we have shown here prove that the ultimate speed limit for the mud insulator to metal transition, which is inherently electronic property, is driven by the sound velocity, which is clearly a structural property, a property of the phonons. Also, what we have shown is that the transition, let's say that the transition that would last a few picoseconds are achievable if you think in terms of application, and if so, this is at least 3 orders of magnitude faster than what we can reach today if we use only electric stimulus. So it's really promising for the future. For MOT devices based on light, we can go to super high frequency operating frequencies, let's say, and also this is super promising for in terms of energy efficiency, because if the shorter the duration of the stimulus, the smaller the energy to induce the transition. And so I would like, with this, I thank you for your attention, and I'm ready to answer your question if you have some. Thanks a lot.
Professor Janod, thank you. Merci beaucoup. Thank you for your talk. I would like people to now prepare some questions. Let's have a look down the list. Who would like to start? Perhaps Mario Rice, do you have a question for Professor Janod?
Hello.
Sorry, I have problem here with my. Can you hear me?
Yes.
Sorry, because I have a new device here, and it was a bit difficult to find the button here. Sorry, I don't have question. Thank you for the speaker for the very nice talk, and thank you. But I don't have a question. Thank you. Thank you a lot.
Thank you, Mario. Okay. Who else have we got today? We've got Alexander. Alexander, do you have a question, please, for the speaker today?
Thank you very much. Very nice talk. Hello, Professor Etienne. Very nice talk. I really enjoyed. I have a question. You mentioned these two different transitions, one that is volatile and the other one is non-volatile transition. But
Yeah.
I don't understand. Probably the non-volatile transition is also a structural transition, probably. But in the case of the non-volatile transition, I couldn't understand well the situation in that case. Maybe if you can explain more about the two cases and what happened from the structural point of view in both cases.
It's a good question because essentially because I cannot answer completely to answer completely. Let me show. Well, maybe let me show this one. So indeed, let's say from the point of view of electric resistance, we can say that we have one transition which is volatile and another one which is volatile in the sense that resistance during the application of the electric pulse lower the transition, but after the pulse, the resistance relaxes back to its initial value. We call that volatile. And the other type of transition is the one which is illustrated here. We have sent the pulse, and after the pulse, the resistance remain low. So for the transition which is non-volatile, we are now quite confident about a conclusion based on this work, the work you show here. We know we have a filamentary conducting channel, if you want. And on the structural point of view, it corresponds to a compression. And we really think that it has to do with mode physics, that it has to do with what happened at the insulator to metal transition. So this is the case of non-volatile transition. Now, what happened? Your question is what happens structurally when during the volatile transition? So it's a super good question, and we ask ourselves this question since many years, and we have in 2 months, well, beginning of February, we have an experiment at the French synchrotron Soleil. We have an experiment where we will synchronize let's say application of electric pulses, and we have synchronized with really now nano-focused X-rays. So we will use X-ray. Sorry, I didn't put the scale. Oh, my mistake. I did not put the scale on this image, but typically the width of this stripe is 20 micron. So the width, the typical size of the filament here is, let's say, 2 to 4 microns. And let's say what we're gonna do in 2 months, we will synchronize application of pulse, and we will do a mapping, structural mapping, because with diffraction, with a beam size of as low as 90 nanometers. So we have good hope to understand whether also during the application of the pulse we have this compressive effect or not. Let's say that's what we expect, but I cannot tell you. I hope I will be able to answer you super convincingly after this first week of February. So that's where we are. But we have in mind that if we see this compressive effect for the non-volatile transition, it's a bit hard to imagine that nothing happened during the volatile transition. You see the way to think about this.
Okay, thank you very much. I can wait for the experiments after that. Thank you very much. Very nice talk. Thank you.
Thanks.
Thank you, Alexander. Let's go next to Gabriela. Gabriela, do you have a question, please, for the speaker?
Hello, Etienne.
Hello.
Thank you very much for your talk. It's very interesting. All this physics applied to such modern stuff about the possibilities of these hardware neural networks. It's the first time I heard something like this. I would like to ask if there are some DFT calculations or I don't know if it's possible to predict, but at least to go along with this investigation, to study, I don't know, these U properties in these transformations, or some comparisons about energy or some parameters?
In fact, well, yes. I don't think I have. I do not think I. Let me check. But I don't think I have. No, I do not. No, I do not have an illustration of the calculation we have done. But yes, we have done. Let's say we have done calculation on the material. On the preceding material to figure out whether it was really a mot insulators. So we have done advanced, well, more than DFT, beyond DFT calculation. We have done a dynamical mean field theory in collaboration with Marcelo Rosenberg, who is working both in Paris and also at the University of Buenos Aires. And the calculation were done by people in Argentina.
Oh.
On the chalcogenide mot insulator that I introduced. And it confirmed that indeed, well, this system have a gap due to electron-electron repulsion and so on. That's the thing. But if the question is, can we use DFT calculation, for example, to predict that when we apply an electric pulse, an electric field, this material will generate a contraction, which is the thing we are contraction of the lattice, for example. This is something much more difficult to do because if you do that, you need to use, let's say, you need to use codes or DFT. You need to have a theory that is able to treat excited state.
Yes.
Which is yes, but we able to treat excited state in strongly correlated material, which is a two level of difficulties that add up to each other, if you want. So so far, let's say that's not what we have done, but I'm not aware of techniques that would allow of conceptual approach that would allow to do that, to treat that easily. Possibly what I have in mind, DMFT, as you might know, dynamical mean field theory, is able to treat. Usually, it's a way to solve the Hubbard Hamiltonian, which is the Hamiltonian that is supposed to describe mot insulators. But clearly, in our case, it's not enough because it contains only the electronic degrees of freedom. So what we would need is we would need a compressible. If you want something like a compressible Hubbard model, we need to be coupled to the phonons, but not to optical phonons, to acoustical phonon, in order to be able to treat the degrees of freedom, which is, well, compressibility.
Oh.
So this is maybe you are aware of that of technique that might be able to do that, but I'm not, to be fair.
No, to phonons, no, I'm not sure. There is a code that deals with excited states. It's called exciting, the German code. But I don't know how they can couple with this phonon, with the phonon part. I think it's a new code, sort of new, not few years, and I don't know the degree of development to do that kind of things. But well, I think it's very interesting to think
Okay.
about. Who
Yeah.
are you? Which is the group in Buenos Aires?
Oh, it was the group. So okay, let me.
Maybe it's
No, the group. Zut,
Lo-
zut, zut, zut.
Lois. What is DFT
Okay,
calculation?
I can tell you in 1 minute. The collaboration we have was with Marcelo Rosenberg, who is working in Paris, but he has collaborators. I will tell you in 1 minute. The people in Buenos Aires. It was. Let me find this. Let me find this. Oh, come on. Yeah, so sorry about the pronunciation. So I think his name is Alberto Kamiai. Um,
I
I
don't
don't want.
know him.
So he's Department of Physics at Ciudad Universitaria in Buenos Aires.
Yeah, there was a very big group, and the boss, I think it's already retired. She's retired, but there was a very big DFT calculation group in Buenos Aires. But
So
I,
here it was beyond. It was it
yes,
was
it's
not DFT, but
not DFT normal.
dynamical.
Yes, of course, of course.
And the other one was I think his first name was Carlos. It's Carlos Asha, also working in Buenos Aires. Yeah.
Okay, thank you very much. It's very interesting. Maybe
No.
I will look for the papers of that kind of stuff
Thank you.
Gabriela, thank you for your question. Okay, let's move on. We've got Alfredo. Alfredo, do you have a question, please, for the speaker?
Thanks for your nice talk. I just want to ask if these structures has similarity with the perovskites.
Well, okay, what I can say, let's say, so I did not, yeah, you're right. I did not comment much about the structure. But in fact, let's say, as I said, the property that we have observed do not depend on a specific structure, a perovskite or something else. It's related to the Mott insulator state. So, for example, the structure of V2O3 is a corundum structure, the same as sapphire, for example. Here, the AM4Q8, it's a structure which derive from the spinel structure. So it's not 1,2,4, but 1,4,8, as you can see, because there is one site which is empty in this system. But generally speaking, let's say all the effect that I discuss here do not depend on a specific structure. It's really related to the question whether your material is it a Mott insulator or not. And if it's a Mott insulator, we can expect the phenomena that I shown here and discuss they are supposed to appear. You see, it's not really related to a specific structure. I don't know if it answered the question.
Yes. This question is because in perovskites, you can change the bandgap depending of the large or the volume of the unit cell. So it's the same trend. If you add a less symmetric structure, the bandgap gets bigger, large. So I think that you are manipulating this behavior of the structure depending of the volume of the unit cell. So it's not just
yeah,
for this kind of structure. You can find this behavior in another structures like perovskites.
I can imagine, but maybe one thing about perovskite. In perovskite, you tune the bandwidth. Usually, it's by tuning the rotation of the octahedra, and well, most of the case it's there. It's not the only reason, but it's one of them. What we are doing here, we are not well. We have no sign that we manipulate we are manipulating the degrees of freedom inside of the unit cell. Here, the effect it's more the compression of the unit cell. You see what happened, and if you keep, let's say, the same geometry but you compress the volume, still you will increase the bandwidth. Of course, I cannot give you more detailed experiment because we did not work on a specific perovskite, and so I cannot prove what I say. But my feeling is that the connection between the electronic degrees of freedom, insulator, metal, and the structure is through the unit cell volume, not degrees of freedom like tilting of the octahedra, which are inside of the unit cell. But okay, it has to be proven in a way because we never investigate directly perovskite, but indeed there are a couple of perovskite that are not insulators. You're right, and we might try to study them. Yes.
And just regarding to the abundance of these structures, so no problem with the elements inside these compounds. Everything is okay, not the prices of these new materials. So you can talk more about this.
So your question is related to abundance of the chemical elements and possible use in microelectronics? Well, yes, good,
Yes.
very good question, of course. What we can say is that, okay, so if we take let's take the example of these two systems that we have here. In fact, especially, well, vanadium, in terms of abundance, vanadium is, let's say, in the middle, is somewhere in the middle. So that it's one element which is not super rare, but on the other hand, it's not silicon or so. So in terms of abundance, vanadium, it's fine because what we have in mind is thin film, so the consumption is not super. We do not consume too much vanadium when we do this thin film deposition. On the other hand, it's true that chromium, it's not a question of abundance, but question of for maybe health issue. Chromium, even when chromium is 3 plus like this, it's not dangerous. I mean, not more dangerous than any other element, but it's well known that when chromium is 6 plus, it can be dangerous. So therefore, it's not probably the best element for application. But we have other possibility, and we might substitute chromium by some other element which play exactly the same game, which result in the same property, and that's something that we are launching. That's something we are, and now if we switch to the next system, well, once again, in microelectronics, I mean, not, let's say, classically, people prefer oxide to chalcogen, but on the other hand, if you maybe you remember uh, what people call phase change material. Phase change material that are used in microelectronics. Intel has made memories 8 years ago. I don't remember the name, but it was memories based on chalcogenides, and they were able to do it, and for the safety issues, it was fine. And for abundance, well, it's the same. We need to consider specific case by specific case. But the good thing about what I discussed, once again, so it's not one particular compound; it's a family. So in fact, the idea is, well, if one mot insulator is not appropriate for the reason you mentioned, it's usually possible to switch to another.
Okay, and the last question is regarding the ambient, the conditions. For example, in perovskite, the problem is the water, the humidity, in order to obtain a better performance of these structures, these devices. So these structures have the same problem or not?
So the question, well, let's say it depends. The sensitivity to moisture or to air is really much lower than the case of perovskite in the example that I gave. But so therefore, I mean, in other words, when we do a thin film of this material, we can keep them in air for weeks or months and reuse them several months after. We did not detect any change in the property we are probing, especially when we are probing well, strain wave with time resolved XRD. We have no moisture or not a lot of degrade. We do not see damage or aging. But also one thing I would like to highlight, if we think about application, here you have a nice example. Our film, it's well, the thin film that we have deposited. It's in collaboration with CEA in France. You see, so at the bottom you have a lot of complicated stuff like transistors and so on. The film is deposited on top of this, but then as you can see, it's covered. It's covered by additional electrode. It's covered by, well, many different layers on top of this. So it's nice because it's a strong protection against, well, humidity or so even if the material was a bit sensitive to moisture, air, aging in a way or another, in real devices, you see, we can clearly see that it can be a bit protected against this by this, well, covering by top electrode and so on. So it's not really this issue is not too serious, let's say.
Well, thanks a lot for your answers to my questions. And
Thank you.
well, congratulations for your work.
Thanks.
Thank you, Alfredo. We're moving down the list to Julio. Julio, do you have any question for Etienne, please?
Hello. Well, I don't think that I can have non-biased questions at the end. Etienne is my former PhD supervisor, but no. Just to say that I hope that my PhD students fellow were as excited about the topic as I was the first time I heard about it. Yeah, it's pretty much all I would say. But thanks.
Thank you, Julio. Oh, we move on now to Ximena. Ximena, do you have any questions from your grouping of people?
Good morning, Professor Stewart and speaker. We don't have any questions from our networks. The people only say thank you for your talk and the interesting topic. Thank you.
Okay,
thank you, Ximena. I think we've lost James. So James has disappeared. Mario has sent his apologies. He's left already. Lewis has left. He's sent thanks. He's texted me to say thank you.
Okay, thank you. I hope he will have his plane.
So I think we have concluded business today. Etienne, do you have anything else to share with us, or to any words that you want to finish with?
Well, so I would like to thank you for your attention, and yeah, well, thanks a lot for your question. I hope it was interesting for you.
Maybe we should put our cameras on, the people that are left here. Etienne, could you stop sharing your screen, and we can fill the screen with people to say thank you?
Of course. Yeah, that's it. Right.
Thank you, everybody. Thank you for formulating questions for Etienne. Thank you, Professor Janod, for your fantastic talk. I have many questions myself, but I can send you an email.
Great. Yeah, let's do it. Let's do it like this.
Thank you.
Okay.
Bye, everybody.